Okay, I will start sharing right away. Welcome, Seth. We're recording and we're just starting to get rolling here. I'm going to do my sharing. Okay, so you should be seeing my screen. Welcome, Mason. Hopefully you'll be able to stay connected. Welcome, Jared. Good to have you in there. We're just getting rolling. I just started recording. I want to just make this general announcements here before we do anything, and that is today the goal is, you probably saw that in my email, we want to show, yes, I guess this will actually be the third day we're spending on this lesson, very important lesson, optimization problems and discussion, and you will not be getting a new assignment. And then tomorrow I'm going to make a presentation to you. So again, really no new lesson. I have a presentation entitled Optimal Design that fits perfectly with where we're right now. So just wanted to make that announcement first. All right? And then a question was asked by one of the students ahead of time. Is there any difference between approaches when the problem asks you to minimize something as opposed to a different problem that asks you to maximize something? Well, when it comes to technique, there's actually no difference, because in both cases, what you're going to want to do is find the derivative, set the derivative equal to 0, and solve. So that technique just is used throughout. The difference is if a function, for example, an upright parabola, one that opens upward, is never going to have a maximum because those arms of the parabola reach up forever. But it will have a minimum. So if I was to take an upward-facing parabola and ask you to find a maximum, well, it's just ridiculous. You can't do it. So, and by the way, I'm not going to do that on tests or quizzes or anything like that. So, bottom line is, the technique is identical. And you probably have noticed that already because there are some of each in the assignment. So, but that's really a good question. Okay, the next thing I wanted to stop off at is I was asked a question about number 3. So let's take a look at number 3 here. Welcome, Sarah. Glad to have you in here. We just going, and we're just taking a look at a question asked by the students to take a look at number 3. See, we lost Seth. Hopefully he can get his way back. So 3, the question is, let me get the wording from the book. Find 2 positive numbers that satisfy these requirements. In number 3, it's the sum of the first and the second is 36. I'm sorry, the sum of the first and twice the second is 36. And you want to make the product a maximum. All right? So, you see how I translated that? The sum of the first and twice the second. So technically, I'm just calling the first number x and the second number y temporarily. Okay? Yes, I know we can't have variables. So over on the side, what you'll see me doing here is finding out another name for y. So I just took the equation from over here, and I'm solving for y. So I subtracted x from both sides, and then I divided both sides by 2. So now I have this new name for y, which you can see I plugged in right there, just in place of y. I'm sorry. Yeah. Okay, and there's another thing going on in this step, and that is they told us what? The product is a maximum. So this is an expression showing you the product of the two. So here's x times the new name for y. That's our function. That's what we want to maximize. All right, so I then multiplied it out in the next step. Yeah, I reversed it. What's x times negative x over 2? It's negative x squared over 2, or negative 1/2 x squared, and x times 18 is 18x. Okay, take the derivative. Nice power rule here. 2 times negative 1/2 is negative 1, so this becomes negative 1x, and then plus 18, set it equal to 0. X is 18. Well, if x is 18, then what's y? Well, you could look right up here, plug in 18 for x. 2 is 9, and 18 minus 9 is 9. So that's the second half of the answer there. So let me just pause. Is there any follow-up to that? First, ask me the question, or anybody else? That was number 3. So find two numbers where the sum of the first and twice the second is 36, and whose product is a maximum. Okay, the next one I'm going to stop off at, I was asked about number 21. So I'm going to buzz over to 21. 21 has a challenge to set up, and I'm going to have to explain what I did here so you figure out what I'm doing. All right, 21. I don't have the problem written out, so I'll just read it here. A home gardener estimates that if she plants 16 apple trees, the average yield will be 80 apples per tree. Because of the size of the garden, every additional tree she plants it'll make the yield, the rate, go down by 4 apples per tree. All right, so let me just show you. I haven't finished reading, but so let's see, how do we explain this? So if you take 16 times 80, we just do that over here. That's where I got the 1280 from. So that's kind of where we are right now. We've got that many trees, so that's the yield. And then I have to take the number of new trees planted, and here's the rate. And let me explain this rate. It says, well, it's currently 80, but for every extra tree you plant, this is my extra expression right here, for every tree you go over 16, that would be T minus, like if I planted 17, how many did I go over? 1. So this is my over 16 amount. For every tree over 16, you lose 4 in the yield. So that's why I wrote 80 to start off with, minus 4 for every tree over 16. That's what this is supposed to say. Now take that rate times the number of trees, and you've got your equation. So in the second line, I started multiplying out this distributive property right here. Negative 4 times t is negative 4t. Negative 4 times negative 16 is plus 64. And then I could combine the 80 and the 64. I take that back. I decided that I went ahead and multiplied right away. I combined them later. So anyway, multiply that whole expression by t. 80 times t, negative 4t times t, and 64 times t. Now I combine the two 80t and 64t into 144t. So I finally have what? My expression for how much of a yield we're going to get. There's my function. Now, good old find the derivative, easy derivative, set the derivative equal to 0, solve for t. So I came up with 18 trees, and that was the first question, right? Let me just check here. How many trees should be planted to maximize the total yield? Answer, 18 trees. Part B, the second question is, what is the maximum yield? So in other words, once you do plant 18 more trees, what will the yield be? And so that's just your original, that's this function with the arrow right here, at 18. And when you plug that in and crank it out, you come up with 1,296 apples. The hardest part, and some of the students that talked to me ahead of the session today agreed with me, that the hardest part of these really in many cases is setting up the equation and getting your variables straight. And somebody else, and then also mentioned, you got to get it down to one variable. In this case, that wasn't a problem. But like if you've got a length and a width, we can't have both an L and a W, so we always have to spend just a small amount doing that substitution. This one we didn't have to worry about that part at least. So follow up on number 21. Anything? Excuse me. Almost through the whole, just a few little things yet. Okay, well, one that always seems to come up, I'm surprised nobody asked about, is number 17. That's a little bit of a setup issue. So I'm going to pick that problem next. So let's get started. I'm going to read this. I don't have the picture in the book, but I drew my own picture. It says a Norman window is constructed by putting a semicircle on top of an ordinary rectangular window. So you see I have the red rectangular window with the black circular part, you know, nice attractive window. They're also incredibly expensive. But anyway, that's a Norman window. Find the dimensions of a Norman window of maximum area if the total perimeter is only 16 feet. So we're limited by the perimeter at 16. That's this guy right here. So that's kind of where we're beginning. And so this perimeter all the way around, including the semicircle, the whole thing has to be a perimeter of 16. By the way, even though a Norman window has to be made up almost for sure with 2 panes of glass, you know, you're going to have a seam going along here. Even though that's the case, I'm assuming the perimeter is just around the outside of the window, okay? That would be another issue we'd have to deal with if that was the situation, but it's not. Okay. So, for the time being, I called the width of the window X and the length, the height of the window Y on the bottom. And then we'll deal with the semicircle also. Well, let's deal with it right now. How does one determine, it would be like a circumference, right? Except it's only half a circle. So what's circumference? Pi times diameter? Okay. But this is only half a circle, so it's pi times diameter divided by 2. So if you look way up here in the corner, you can see me figuring out that circumference. There's pi times the radius Hang on a minute. No, that's me finding the area. Excuse me. So here's the perimeter. We've got two y's because there's one on each side. We've got one x on the bottom. And then we have the circumference, pi times that diameter divided by 2. Okay, add those up, and that perimeter must be 16. So that's a good beginning point. As you know, though, we can't have two variables, can we? So you'll see that what I'm doing here is trying to find another expression for y. So what I did is I'm getting the y alone by subtracting x from both sides and by subtracting this pi x over 2 from both sides. And then divide both sides by 2. I now have an alternate way to say y. Okay, so now that I've got my x dimension, I've got my y dimension. Now it's time to get the area of the window, because that was the problem's mission, to maximize the area. Okay, so you can see I'm starting to write this expression. So how does one find the area of a Norman window? Well, you take the area of the rectangle plus the area of the semicircle, right? So what's the area of the rectangle? X times y, right? Except we don't want to use y, we want to use this expression here for y. So here's the area of the rectangle. X times the new expression for y. Plus, and now I got to put the area of the semicircle. Remember, how do you find the area of a